March 24, 1944, 28,000 feet above Rabaul. Hauptmann Heinrich Erler pulled his Focke-Wulf 190 into a climbing turn, scanning the crystalline Pacific sky for the American fighter sweep his radar operators had detected. 24 fighters of Jagdgeschwader 200, Germany's most experienced tropical warfare unit, climbed toward what intelligence reports described as a new American carrier fighter. What Erler couldn't see through the morning haze was a formation of 12 bent-winged aircraft diving toward his position at speeds that defied every assumption German aerodynamic theory held about fighter aircraft design. At 32,000 feet, Major Gregory Boyington rolled his F4U Corsair into a near-vertical dive, the distinctive inverted gull wings biting into the thin air with an efficiency that Chance Vought's engineers had perfected through revolutionary design. The massive double Wasp engine, generating 2,000 horsepower, pulled the Corsair past 450 miles per hour in a controlled dive that would have torn the wings off any German fighter. What the Luftwaffe pilots below were about to experience was not just superior American engineering, but a fundamental revolution in aircraft design that rendered their understanding of aerodynamics obsolete. The mathematics of terror were written in the Corsair's unique wing configuration. While German fighters achieved their performance through conventional straight-wing designs that imposed limiting factors on propeller clearance and landing gear length, Vought's engineers had solved these problems through an inverted gull wing that allowed unprecedented combinations of power, propeller efficiency, and structural strength. The bent wings that looked so unusual to German observers were actually the solution to engineering problems that German designers had never successfully addressed. The Corsair's development had begun in 1938, when the US Navy issued specifications for a carrier fighter that could exceed 400 miles per hour while maintaining the structural strength required for carrier operations. Chance Vought's chief designer, Rex Beisel, recognized that conventional fighter design philosophy could not achieve these seemingly contradictory requirements. The massive Pratt & Whitney R2800 double Wasp engine needed for such performance required a propeller 13 feet 4 inches in diameter, far too large for conventional landing gear arrangements aboard aircraft carriers. Beisel's solution was revolutionary in its simplicity and devastating in its effectiveness. The inverted gull wing, bending downward from the fuselage before angling back up toward the wingtips, allowed the main landing gear to be shortened while maintaining adequate propeller clearance. This configuration also reduced drag by enabling the wing root to meet the fuselage at optimal angles while providing the structural strength needed for high-G maneuvers and carrier landings. German aerodynamicists, constrained by conventional design thinking, had never conceived such a radical approach to fighter aircraft engineering. The first XF4U prototype flew on May 29, 1940, immediately demonstrating performance that exceeded design specifications. During its fourth test flight, the prototype became the first single-engine American fighter to exceed 400 miles per hour in level flight, reaching 405 miles per hour at 25,000 feet. This achievement represented a quantum leap in fighter performance that German intelligence would not fully comprehend until their pilots faced Corsairs in combat. Production of the F4U began in 1941, but initial carrier trials revealed handling characteristics that required extensive modification. The Corsair's powerful engine and unique wing configuration created torque effects and landing characteristics that challenged even experienced carrier pilots. While the Navy initially rejected the aircraft for carrier operations, the Marine Corps recognized its potential for land-based operations and became the Corsair's first operational user. By early 1943, Marine Fighting Squadron 124, commanded by Major William Giese, had become the first unit to fly combat missions with the Corsair. Operating from Henderson Field on Guadalcanal, VMF 124 immediately demonstrated the aircraft's superiority over Japanese fighters. The combination of speed, firepower, and diving performance created tactical advantages that Japanese pilots could not counter with existing aircraft or tactics. The Corsairs' armament represented another revolution in fighter aircraft design. 6.50 caliber Browning machine guns, mounted in the outer wing panels, provided devastating firepower that could destroy enemy aircraft with brief bursts. Each gun carried 400 rounds, giving the Corsair 2,400 rounds total and approximately 20 seconds of firing time. German fighters, typically armed with a combination of machine guns and cannon, could not match the sustained firepower that the Corsair's standardized heavy machine gun battery provided. The structural strength required for the Corsair's bent wing configuration resulted in an aircraft that could withstand G-forces that would destroy conventional fighters. Load testing revealed that the Corsair could sustain 11G pullouts without structural failure, far exceeding the capabilities of German aircraft designed for 6G maximum loads. This structural superiority enabled dive attack profiles that German fighters could not follow without risking catastrophic failure. Engine cooling systems incorporated into the Corsair's design included innovative solutions that German engineers had never developed. The massive oil coolers required for the 2,000 horsepower double Wasp were integrated into the wing root design, using the bent wing configuration to optimize airflow while maintaining structural integrity. German fighters, struggling with cooling problems that limited engine performance, could not achieve comparable power-to-weight ratios. The psychological impact of the Corsair's appearance proved as significant as its performance advantages. The bent wings, long nose, and massive propeller created a distinctive silhouette that became synonymous with American air superiority. German pilots developed an immediate recognition of the Corsair's unique profile, often breaking off attacks when they identified the characteristic wing configuration of what they learned to call der Nickflügel, the bent wing. Training programs for Corsair pilots emphasized the aircraft's unique capabilities while addressing its demanding handling characteristics. Marine pilots learned to exploit the Corsair's diving speed and firepower while managing the powerful engine's torque effects and the aircraft's tendency towards stall departure. This specialized training created pilots who could extract maximum performance from the Corsair's revolutionary design, multiplying its technological advantages through superior tactics. Combat tactics developed specifically for the Corsair emphasized the aircraft's speed and diving performance over traditional fighter maneuvering. The boom and zoom technique, diving on enemies from altitude and using speed to escape before they could respond, proved devastatingly effective against German fighters optimized for turning combat. Japanese and German pilots, trained for dogfighting, found their tactical doctrine useless against Corsairs that refused to engage in traditional aerial combat. The manufacturing challenge of producing the Corsair's complex wing structure required innovative production techniques that pushed American industry to new levels of precision. The bent wing configuration demanded exact tolerances in wing twist, dihedral angles, and structural joints that conventional aircraft manufacturing had never required. Vought developed specialized tooling and assembly procedures that enabled mass production of this sophisticated design. Quality control procedures for Corsair production included structural testing that verified the integrity of each aircraft's unique wing configuration. Load testing, vibration analysis, and flight testing ensured that production aircraft met the exacting standards required for the bent wing design. German aircraft production, increasingly hampered by resource shortages and simplified manufacturing, could not achieve comparable quality standards. The logistics of supporting Corsair operations included spare parts and maintenance procedures specifically designed for the aircraft's unique configuration. Specialized tools, replacement components, and maintenance manuals addressed the complexity of the bent wing structure while enabling field maintenance that kept aircraft operational under combat conditions. German logistics systems, strained by multiple aircraft types and limited resources, could not provide comparable support for their increasingly complex fighter designs. By late 1943, Corsair units were achieving kill ratios that astounded both American and German Air Force analysts. VMF 214, the famous Black Sheep Squadron, commanded by Major Gregory Boyington, achieved 203 confirmed aerial victories while losing only 17 aircraft in combat. These ratios reflected not just pilot skill, but the technological superiority that the Corsairs' revolutionary design provided over conventional fighter aircraft. German intelligence efforts to understand Corsair capabilities included examination of crashed aircraft and interrogation of captured pilots. Technical analysis revealed the sophistication of the bent wing design and the engineering solutions it provided, but German industry lacked the manufacturing capability and resources to develop comparable aircraft. The Corsairs' technological advantages were not just design innovations, but manufacturing achievements that German wartime production could not duplicate. Combat reports from German pilots encountering Corsairs consistently described aircraft performance that seemed to violate aerodynamic principles. High-speed dives that continued far beyond the safety limits of German fighters, sustained firepower that exceeded German ammunition capacity, and structural integrity that survived maneuvers fatal to conventional aircraft. These reports documented the Corsairs' technological superiority while revealing German confusion about American engineering capabilities. The bent wing configuration enabled fuel tank arrangements that gave the Corsair range capabilities German fighters could not match. Internal fuel capacity of 237 gallons, combined with external tank options, provided operational radius that allowed American fighters to escort bombers deep into German-controlled territory. German fighters, limited by fuel capacity and consumption rates, could not sustain comparable operational tempo or range. Engine management systems developed for the Corsair's massive double WASP included automated controls that optimized performance while preventing engine damage from overboost or overheating. These systems enabled pilots to focus on combat tactics rather than engine management, providing significant advantages over German fighters that required constant attention to engine parameters. The technological sophistication of American engine controls multiplied pilot effectiveness while reducing training requirements. The development of carrier-capable variants addressed the Navy's initial concerns about the Corsair's landing characteristics while maintaining the performance advantages of the bent wing design. Modified landing gear, improved forward visibility, and refined handling characteristics enabled carrier operations that multiplied the Corsair's strategic impact. German naval aviation, limited to shore-based operations, could not achieve comparable operational flexibility. Testing programs for Corsair variants included high-speed dives that explored the limits of the bent wing design under extreme conditions. Test pilots regularly dove Corsairs beyond 500 miles per hour, demonstrating structural integrity that exceeded any German fighter's capabilities. These test programs validated design decisions while providing data for continuous improvement of an already revolutionary aircraft. The industrial achievement of mass-producing the Corsair's complex structure demonstrated American manufacturing capabilities that German planners had consistently underestimated. Over 12,500 Corsairs were built during the war, each requiring precision manufacturing of the demanding bent wing configuration. German fighter production, increasingly simplified to reduce manufacturing complexity, could not approach these production volumes while maintaining comparable structural sophistication. Pilot training facilities for the Corsair included specialized instruction in managing the aircraft's unique characteristics while exploiting its performance advantages. Training emphasized the bent wing's structural strength, enabling aggressive tactics that would destroy conventional fighters. German pilot training, increasingly abbreviated due to fuel shortages, could not provide comparable preparation for high-performance aircraft operations. The strategic impact of Corsair deployment extended beyond individual combat encounters to influence the entire character of Pacific air warfare. American control of airspace, enabled by Corsair superiority over Japanese fighters, allowed unrestricted bomber operations and amphibious assaults. German forces in the Pacific, limited to defensive operations, could not challenge American air superiority established through Corsair technological dominance. Research and development programs supporting Corsair improvement included wind tunnel testing, structural analysis, and performance optimization that continuously enhanced the aircraft's capabilities. University laboratories, industrial research facilities, and military testing organizations collaborated to maximize the bent wing design's potential. German research efforts, limited by resources and security restrictions, could not achieve comparable technological development rates. The electronic systems integrated into later Corsair variants included radio equipment, navigation aids, and gunsight technology that multiplied pilot effectiveness in combat. These systems, while primitive by modern standards, provided capabilities that German fighters lacked due to electronics industry limitations and resource priorities. The systematic integration of advanced electronics with revolutionary aerodynamics created combined advantages that German technology could not match. Medical services supporting Corsair operations included flight surgeons trained in high-performance aircraft physiology and equipped with facilities that could treat injuries specific to high-G maneuvering. The structural strength that enabled aggressive Corsair tactics also subjected pilots to physical stresses that required specialized medical support. German medical services, limited by traditional approaches and resource constraints, could not provide comparable care for high-performance fighter pilots. The environmental challenges of Pacific operations required modifications to the Corsair's design that demonstrated American engineering flexibility and manufacturing capability. Tropical climate adaptations, saltwater corrosion protection, and maintenance procedures for primitive base conditions enabled sustained operations throughout the Pacific theater. German aircraft, designed for European conditions, could not achieve comparable operational availability in Pacific environments. Intelligence analysis of Corsair capabilities revealed German recognition that American fighter design had achieved fundamental breakthroughs that rendered existing Luftwaffe aircraft obsolete. Technical reports acknowledged the superiority of the bent wing configuration while admitting that German industry could not develop comparable solutions within wartime constraints. The Corsair had not just achieved tactical superiority, but demonstrated technological leadership that German aviation could not challenge. The manufacturing innovations required for Corsair production included precision metalworking, advanced welding techniques, and quality control systems that established new standards for aircraft construction. These techniques, developed for military necessity, influenced post-war aviation manufacturing worldwide. German aircraft production, increasingly simplified and resource-constrained, fell further behind American technological capabilities with each production innovation. Training programs that produced Corsair maintenance personnel included technical education that German military schools could not provide. Understanding of advanced metallurgy, precision mechanics, and structural engineering enabled American maintenance crews to keep sophisticated aircraft operational under combat conditions. German maintenance training, limited by accelerated schedules and resource shortages, could not produce comparable technical expertise. The systematic approach to Corsair deployment included tactical doctrine, logistical support, and training programs that maximized the aircraft's revolutionary capabilities. This integrated approach transformed technological advantages into sustained combat superiority that German forces could not counter through tactical innovation or operational excellence. The bent wing had become more than aerodynamic innovation. It was the foundation for comprehensive air superiority. The psychological transformation of Luftwaffe pilots when encountering Corsairs revealed the profound impact that revolutionary aircraft design could have on veteran aviators. Hauptmann Heinrich Erler, a decorated pilot with 209 confirmed victories on the Eastern Front, found his tactical expertise useless when facing aircraft that seemed to violate every principle of aerodynamics he understood. His combat report, filed after a devastating encounter with Marine Corsairs over Rabaul, captured the disorientation that the bent wing fighter created among Germany's most experienced pilots. The American fighter approached from above at speeds I estimated to exceed 400 miles per hour, Erler wrote. When I attempted evasive maneuvers, the enemy aircraft followed through turns that should have caused structural failure. The wings, bent in an impossible configuration, seemed to strengthen rather than weaken under load. Our tactics, proven against every Allied fighter, were useless against this machine that defied engineering logic. The technical intelligence gathered by German engineers from crashed Corsairs revealed the sophistication of American aerodynamic research that had produced the inverted gull wing configuration. Structural analysis showed that the bent wing actually distributed stress loads more efficiently than conventional straight-wing designs, enabling the aircraft to survive maneuvers that would destroy traditional fighters. German engineers recognized the innovation but lacked the manufacturing resources and time necessary to develop comparable designs. Professor Ernst Heinkel, designer of many German fighter aircraft, examined captured Corsair components and admitted in classified reports that American engineering had achieved breakthroughs that German aviation had not anticipated. The integration of structural strength with aerodynamic efficiency represented by the bent wing design had solved fundamental problems that German designers were still struggling to address. His technical assessment concluded that the Corsair represented a generational advance in fighter aircraft design. The manufacturing complexity of the Corsair's wing structure required precision tooling and quality control systems that demonstrated American industrial capabilities far beyond German wartime production. Each wing assembly demanded exact tolerances in the joint between the downward-angled root section and the upward-angled outer panels. This precision manufacturing enabled the structural integrity that made the Corsair's high-speed diving attacks possible, while maintaining the aerodynamic efficiency needed for sustained high-speed flight. Combat film analysis conducted by German intelligence revealed the tactical revolution that the Corsair's bent wing design had created. Frame-by-frame examination of gun camera footage showed Corsairs maintaining structural integrity through maneuvers that would have destroyed German fighters. High-speed dives followed by violent pullouts demonstrated engineering capabilities that German military aviation had not achieved despite years of advanced development programs. The engine integration achieved through the Corsair's bent wing configuration enabled power-to-weight ratios that German fighters could not match with conventional designs. The massive Pratt & Whitney R2800 double Wasp, generating 2,000 horsepower, was optimally positioned within the aircraft structure to minimize drag while maximizing cooling efficiency. German engines, limited by cooling problems and installation constraints, could not achieve comparable power output in practical fighter applications. Pilot testimonies from German aircrew who survived encounters with Corsairs consistently described aircraft performance that seemed impossible according to their understanding of fighter capabilities. The ability to maintain high speeds through violent maneuvers combined with structural strength that survived combat damage that would down German fighters created an impression of technological superiority that undermined German pilot confidence in their own aircraft. Oberst Johannes Steinhoff, commanding JG-77 during Mediterranean operations, observed Corsair tactics and recognized that German fighter doctrine required fundamental revision when facing aircraft with such superior diving performance. Traditional German tactics, emphasizing climbing ability and turning performance, proved ineffective against Corsairs that could dictate engagement terms through speed and structural strength. His tactical analyses influenced Luftwaffe doctrine, but could not overcome the fundamental technological disadvantages German fighters faced. The logistics of maintaining Corsair operations in forward Pacific bases demonstrated American organizational capabilities that supported technological superiority with systematic efficiency. Mobile maintenance units could perform complex repairs on the sophisticated bent wing structure using standardized tools and replacement parts available throughout the theater. German maintenance capabilities, increasingly limited by parts shortages and simplified repair procedures, could not provide comparable support for advanced aircraft designs. Training programs developed specifically for Corsair operations included instruction in exploiting the aircraft's unique capabilities while managing its demanding performance characteristics. Pilots learned to use the structural strength of the bent wing design to execute aggressive maneuvers that would be suicidal in conventional fighters. German pilot training, accelerated by combat losses and limited by fuel shortages, could not provide comparable preparation for high-performance aircraft operations. The communication systems integrated into Corsair operations enabled coordination that multiplied the effectiveness of individual aircraft advantages. Radio equipment, navigation aids, and tactical coordination procedures allowed Corsair formations to concentrate their superior performance against German fighters that lacked comparable command and control capabilities. German communications, limited by equipment shortages and security vulnerabilities, could not achieve systematic coordination that optimized aircraft performance. Research and development programs supporting Corsair improvement included continuous refinement of the bent wing design based on combat experience and scientific analysis. Wind tunnel testing, structural analysis, and performance optimization ensured that the aircraft's revolutionary configuration was constantly enhanced. German research efforts, disrupted by strategic bombing and resource limitations, could not maintain comparable development programs for advanced fighter designs. The environmental adaptations required for Corsair operations in the Pacific Theater included modifications that demonstrated American engineering flexibility and manufacturing responsiveness. Tropical climate protection, saltwater corrosion resistance, and maintenance procedures for primitive base conditions enabled sustained operations throughout diverse operational environments. German aircraft, designed for European conditions, could not achieve comparable operational availability when deployed outside their intended operating environment. Electronic warfare capabilities integrated into later Corsair variants included radio equipment and navigation systems that provided tactical advantages German fighters could not match. While primitive by modern standards, these electronic systems multiplied pilot effectiveness and enabled coordination that German aircraft lacking comparable electronics could not achieve. The systematic integration of electronics with revolutionary aerodynamics created combined advantages that German technology could not counter. Counterintelligence operations protected the technological secrets of the Corsair's bent wing design, while gathering intelligence about German attempts to develop comparable aircraft. Security measures ensured that manufacturing techniques, structural details, and performance characteristics remained classified despite German espionage efforts. American technical intelligence derived from captured German aircraft and documents provided insights that guided Corsair development while revealing German technological limitations. The industrial achievement of mass-producing over 12,500 Corsairs during the war demonstrated American manufacturing capabilities that German planners had never comprehended. Each aircraft required precision assembly of the complex bent wing structure, along with integration of sophisticated engine, armament, and control systems. German fighter production, increasingly simplified to maintain output levels, could not approach these production volumes while achieving comparable technological sophistication. Medical services supporting Corsair operations included specialized training for flight surgeons in treating injuries related to high-G maneuvering and high-speed flight. The structural strength that enabled aggressive Corsair tactics also subjected pilots to physical stresses that required advanced medical understanding and treatment capabilities. German aviation medicine, limited by traditional approaches and resource constraints, could not provide comparable care for high-performance fighter operations. Quality control procedures for Corsair production included structural testing that verified the integrity of each aircraft's bent wing configuration under extreme load conditions. Test protocols validated that production aircraft could withstand the combat stresses that the design's structural advantages enabled. German quality control, increasingly compromised by resource shortages and accelerated production schedules, could not maintain comparable standards for advanced aircraft manufacturing. The strategic impact of Corsair deployment extended throughout the Pacific theater and influenced the entire course of naval aviation warfare. American air superiority, established through Corsair technological dominance over Japanese fighters, enabled unrestricted bomber operations and amphibious assaults that systematically reduced Japanese defensive capabilities. German naval aviation, limited by resource constraints and technological disadvantages, could not achieve comparable strategic impact. Fuel systems developed for the Corsairs' high-performance operations included innovations that enabled sustained combat operations while maintaining safety standards appropriate for the aircraft's aggressive mission profiles. Advanced fuel management systems, fire suppression equipment, and crash-worthy tank designs reflected the engineering sophistication required to support revolutionary aircraft performance. German fuel systems, simplified by resource limitations, could not provide comparable capabilities for high-performance operations. The aerodynamic research that produced the bent wing configuration included wind tunnel testing and mathematical analysis that represented the cutting edge of 1940s aviation science. Systematic investigation of wing loading, stress distribution, and airflow characteristics enabled optimization of the revolutionary design. German aerodynamic research, while technically sophisticated, was increasingly limited by computational resources and testing facility availability. Intelligence analysis of German fighter development revealed recognition that American aircraft design had achieved fundamental advances that Luftwaffe technology could not match within wartime constraints. Technical reports acknowledged Corsair superiority while documenting unsuccessful attempts to develop German aircraft with comparable performance characteristics. The bent wing design had established American technological leadership that German aviation could not challenge. Manufacturing innovations required for Corsair production included precision welding techniques, advanced metallurgy, and assembly procedures that set new standards for aircraft construction quality. These manufacturing advances, developed for military necessity, influenced post-war aviation industry development worldwide. German manufacturing, increasingly constrained by material shortages and simplified production methods, fell progressively behind American technological capabilities. Training facilities for Corsair maintenance personnel included technical schools that provided education in advanced aircraft systems, precision manufacturing tolerances, and complex repair procedures. American maintenance training created technicians capable of supporting sophisticated aircraft operations under combat conditions. German maintenance training, limited by accelerated schedules and resource constraints, could not provide comparable technical education for advanced aircraft support. The systematic approach to Corsair tactical employment included doctrine development, pilot training, and logistical support that maximized the aircraft's revolutionary capabilities through coordinated implementation. American tactical innovation transformed technological advantages into sustained combat superiority that German forces could not counter through operational excellence or tactical adaptation. The bent wing had become the foundation for comprehensive air dominance. Combat statistics from Corsair operations revealed kill ratios that documented the aircraft's technological superiority over German and Japanese fighters. Marine and Navy Corsair units consistently achieved victory ratios exceeding 10-1 against enemy aircraft, reflecting not just pilot skill, but the fundamental advantages that revolutionary design provided. German fighter units, despite experienced pilots and tactical expertise, could not achieve comparable success rates when facing technologically superior opponents. The post-war analysis of Corsair effectiveness confirmed that the bent wing design had achieved one of aviation history's most significant technological breakthroughs. Engineering studies validated the structural and aerodynamic principles that had enabled the aircraft's superior performance, while documenting the manufacturing innovations necessary for practical implementation. German post-war aviation development incorporated lessons learned from American technological leadership established through Corsair innovation. Pilot testimonies from both Allied and Axis aircrews confirmed that the Corsair had fundamentally altered the character of fighter combat through technological superiority that rendered traditional tactical doctrine obsolete. American pilots described confidence in aircraft that could survive maneuvers and combat damage that would destroy conventional fighters. German pilots acknowledged aircraft performance that exceeded their ability to counter through skill or tactical innovation. The environmental testing programs that validated Corsair operations under diverse conditions included extreme weather trials, high-altitude performance verification, and structural stress testing that demonstrated the robustness of the bent wing design. These programs ensured that revolutionary aircraft performance remained reliable under operational conditions that challenged conventional aircraft capabilities. German testing programs, limited by fuel availability and facility access, could not conduct comparable validation of advanced aircraft designs. Research programs supporting Corsair development included university collaborations, industrial research partnerships, and military testing organizations that created systematic innovation capabilities. This coordinated approach to technological development ensured continuous improvement of already revolutionary aircraft performance. German research efforts, increasingly isolated and resource-constrained, could not maintain comparable development programs for advanced aviation technology. The logistics network supporting Corsair operations included supply chains that delivered spare parts, ammunition, and fuel to forward bases throughout the Pacific Theater. Mobile maintenance capabilities, standardized repair procedures, and systematic inventory management enabled sustained operations regardless of geographic isolation or primitive base conditions. German logistics, strained by extended supply lines and resource limitations, could not provide comparable support for advanced aircraft operations. Electronic systems integration in later Corsair variants included navigation equipment, communication systems, and fire control devices that multiplied pilot effectiveness while reducing training requirements. The systematic incorporation of electronic aids with revolutionary aerodynamics created combined capabilities that German aircraft, lacking comparable electronics, could not achieve. American electronics industry capabilities enabled aircraft system integration that German technology could not match. Counter-battery operations conducted by Corsair units included systematic destruction of German airfields, supply installations, and support facilities using the aircraft's superior speed and firepower. These attacks, enabled by the Corsair's performance advantages, degraded German fighter capabilities while demonstrating the strategic impact of technological superiority. German defensive measures, limited by resource constraints and technological disadvantages, could not effectively counter Corsair offensive operations. The scientific approach to Corsair performance optimization included systematic data collection, statistical analysis, and engineering refinement that continuously enhanced aircraft capabilities. Flight testing programs, combat data analysis, and engineering studies ensured that the bent wing design achieved maximum potential through scientific development methods. German aircraft development, increasingly constrained by wartime pressures, could not maintain comparable scientific approaches to performance optimization. Manufacturing quality assurance for Corsair production included inspection procedures, testing protocols, and statistical quality control that ensured each aircraft met exacting performance standards. The precision manufacturing required for the bent wing configuration demanded quality systems that German wartime production could not achieve. American manufacturing excellence transformed innovative design into reliable operational capability that German industry could not duplicate. Training programs for Corsair pilots included specialized instruction in high-speed flight, structural limitations, and tactical employment that maximize the aircraft's revolutionary capabilities. This systematic approach to pilot education created aircrews who could extract maximum performance from advanced aircraft while managing the unique characteristics of the bent wing design. German pilot training, accelerated by combat losses and limited by resource shortages, could not provide comparable preparation for advanced aircraft operations. The strategic implications of Corsair technological superiority extended beyond immediate tactical advantages to influence the entire character of Pacific air warfare. American air dominance, established through revolutionary aircraft design, enabled unrestricted operations that systematically reduced Axis defensive capabilities. German forces, unable to challenge American technological leadership, were forced into increasingly desperate defensive strategies that could only delay inevitable defeat. The legacy of the Corsair's bent wing design influenced post-war aircraft development worldwide, establishing design principles and manufacturing techniques that shaped modern aviation. The revolutionary configuration that had terrorized Luftwaffe pilots became the foundation for advanced aircraft systems that continue to influence contemporary aerospace engineering. German engineers studying American technological achievements after the war acknowledged that the bent wing Corsair had demonstrated engineering capabilities that represented a generational advance in aviation technology. The psychological impact of facing Corsairs proved as devastating to German morale as the aircraft's physical capabilities were to German aircraft. Luftwaffe pilots who had dominated European skies found themselves helpless against American fighters that seemed to violate the laws of physics. The bent wings that had initially appeared unusual became symbols of American technological superiority that German pilots learned to fear. When the distinctive gull-wing silhouette appeared on the horizon, experienced German aviators knew they faced aircraft that could outperform anything in the Luftwaffe inventory. The mathematical precision of the Corsairs' engineering had conquered the skies through revolutionary design that transformed the possible into the inevitable. German pilots had panicked not because they lacked courage, but because they faced technology that rendered their skill and experience irrelevant. The bent wings had spoken with the voice of American industrial might, and their message was clear. The age of technological warfare had begun, and those who mastered its secrets would rule the skies. The structural engineering achievement, represented by the Corsair's inverted gull-wing configuration, required mathematical calculations that pushed 1940s engineering to its limits. Each wing assembly demanded precise analysis of stress distribution, load factors, and material properties that German engineering education had not fully developed. American engineering schools, working closely with aircraft manufacturers, had created educational programs that produced engineers capable of designing and building aircraft that German technical schools could not match. Wind tunnel testing programs supporting Corsair development included sophisticated facilities that could simulate flight conditions up to and beyond the aircraft's maximum performance envelope. The National Advisory Committee for Aeronautics operated wind tunnels capable of testing scale models at speeds exceeding 500 miles per hour, validating design decisions before prototype construction. German wind tunnel facilities, while technically advanced, lacked the capacity and instrumentation necessary for comparable testing of revolutionary aircraft designs. The metallurgical advances required for Corsair wing construction included aluminum alloys and heat treatment processes that provided strength-to-weight ratios superior to conventional aircraft materials. American aluminum industry capabilities enabled production of specialized alloys optimized for the demanding stress patterns of the bent wing configuration. German metallurgy, limited by raw material shortages and simplified production methods, could not achieve comparable material properties in wartime manufacturing. Flight testing protocols for Corsair development included systematic exploration of the aircraft's performance envelope under conditions that would have destroyed conventional fighters. Test pilots regularly subjected prototype aircraft to maneuvers exceeding 8G while diving at speeds approaching 500 miles per hour. These extreme tests validated the structural integrity that enabled combat tactics impossible for German fighters designed to more conservative standards. The precision manufacturing required for Corsair wing assembly included tooling and jigs that maintained tolerances measured in thousandths of an inch throughout the complex bent wing structure. Each wing required exact alignment of the downward-angled center section with the upward-angled outer panels, creating joints that could withstand extreme combat loads. German manufacturing, increasingly simplified to maintain production rates, could not achieve the precision necessary for comparable structural sophistication. Electronic systems integration in advanced Corsair variants included radar equipment, improved radio systems, and navigation aids that multiplied pilot effectiveness while reducing workload. The AN/APS-6 radar, fitted to night fighter variants, provided detection capabilities that German aircraft electronics could not match. American electronics industry capabilities enabled systematic integration of advanced systems that German technology, limited by component shortages and simplified designs, could not achieve. Training programs for Corsair test pilots included specialized education in high-speed flight, structural stress analysis, and emergency procedures specific to the aircraft's unique characteristics. Test pilot schools taught mathematical principles of flight testing, data collection techniques, and systematic approaches to performance evaluation. German test pilot training, while producing skilled aviators, could not provide comparable scientific education in advanced aircraft evaluation. The industrial coordination required for Corsair production included systematic integration of hundreds of subcontractors, producing components to exacting specifications. Supply chain management, quality control coordination, and delivery scheduling enabled mass production of sophisticated aircraft without compromising engineering standards. German production coordination, increasingly disrupted by strategic bombing and resource shortages, could not maintain comparable industrial integration. Maintenance training programs for Corsair technicians included technical education in advanced aircraft systems, precision assembly procedures, and troubleshooting techniques specific to the bent wing configuration. These programs produced maintenance personnel capable of supporting sophisticated aircraft operations under combat conditions. German maintenance training, accelerated by personnel shortages and limited by resource constraints, could not provide comparable technical education. The strategic bombing campaign against German aircraft production facilities demonstrated American commitment to preventing development of fighters that might challenge Corsair superiority. Systematic attacks on German research facilities, manufacturing plants, and testing installations disrupted development programs that might have produced aircraft with performance approaching Corsair capabilities. German aircraft development, increasingly constrained by facility destruction and personnel losses, could not maintain research programs necessary for technological competition. Intelligence operations protecting Corsair technological secrets included comprehensive security measures that prevented German access to design details, manufacturing techniques, and performance characteristics. Classification systems, personnel screening, and facility security ensured that revolutionary aircraft technology remained protected despite German espionage efforts. American counterintelligence, supported by advanced communication security, maintained technological advantages through systematic protection of industrial secrets. The fuel systems designed for Corsair high-performance operations included innovations in tank design, fuel management, and fire suppression that enabled sustained combat operations while maintaining safety standards. Advanced fuel pumps, pressurization systems, and automatic fuel management enabled pilots to focus on combat tactics rather than fuel system operation. German fuel systems, simplified by resource limitations and manufacturing constraints, could not provide comparable capabilities for high-performance aircraft operations. Combat data analysis from Corsair operations included systematic collection of performance information, tactical effectiveness studies, and engineering evaluations that guided continuous aircraft improvement. Statistical analysis of combat encounters, mechanical reliability studies, and pilot feedback created databases that influenced design modifications and operational procedures. German combat data collection, limited by communication difficulties and organizational problems, could not provide comparable systematic analysis for aircraft development. The environmental testing programs validating Corsair operations under extreme conditions included tropical climate trials, high-altitude performance verification, and structural endurance testing that demonstrated the aircraft's operational versatility. These programs ensured that revolutionary performance remained reliable under conditions that challenged conventional aircraft capabilities. German environmental testing, limited by fuel availability and facility access, could not conduct comparable validation of advanced aircraft designs. Manufacturing quality control for Corsair production included statistical sampling, mechanical testing, and systematic inspection procedures that ensured each aircraft met performance standards. Quality assurance programs validated structural integrity, system functionality, and assembly precision throughout the production process. German quality control, increasingly compromised by accelerated production schedules and resource shortages, could not maintain comparable standards for advanced aircraft manufacturing. The communication systems supporting Corsair operations included VHF radio equipment, navigation aids, and coordination networks that enabled tactical integration impossible for German fighters. Clear communication at extended ranges, secure frequency management, and systematic coordination procedures multiplied the effectiveness of individual aircraft advantages. German communications, limited by equipment capabilities and security vulnerabilities, could not achieve comparable tactical coordination. Research and development programs supporting Corsair advancement included university partnerships, industrial collaborations, and military research organizations that created systematic innovation capabilities. Coordinated research efforts ensured continuous improvement of aircraft performance while developing technologies for future applications. German research programs, disrupted by facility destruction and personnel limitations, could not maintain comparable development capabilities for advanced aviation technology. The logistics achievement of supporting Corsair operations throughout the Pacific Theater included supply networks that delivered spare parts, ammunition, and fuel to forward bases regardless of geographic isolation. Mobile maintenance units, standardized repair procedures, and systematic inventory management enabled sustained operations under primitive conditions. German logistics, strained by extended supply lines and transportation limitations, could not provide comparable support for advanced aircraft operations. Electronic warfare capabilities integrated into Corsair operations included radio direction finding, communication security, and primitive jamming systems that provided tactical advantages German aircraft could not counter. These capabilities, while basic by modern standards, created additional complications for German forces already struggling with American technological superiority. German electronic warfare, limited by equipment shortages and technical limitations, could not achieve comparable capabilities. The systematic approach to pilot training for Corsair operations included standardized curricula, advanced flight training, and tactical instruction that maximized the aircraft's revolutionary capabilities. Training programs emphasized the unique characteristics of the bent wing design while developing tactical skills that exploited technological advantages. German pilot training, accelerated by combat losses and limited by fuel shortages, could not provide comparable preparation for advanced aircraft operations. Manufacturing innovations developed for Corsair production included automated assembly techniques, precision welding methods, and quality control systems that established new standards for aircraft construction. These innovations, created for military necessity, influenced post-war aviation manufacturing worldwide while demonstrating American industrial capabilities. German manufacturing, increasingly constrained by resource limitations and simplified production methods, could not achieve comparable technological advancement. The strategic implications of Corsair technological superiority extended beyond immediate tactical advantages to influence Allied strategy throughout the Pacific War. American confidence in air superiority, established through revolutionary aircraft design, enabled aggressive operational planning that systematically reduced Japanese defensive capabilities. German strategic planning, constrained by recognition of technological disadvantages, was forced into increasingly defensive approaches. Intelligence analysis of German attempts to develop aircraft comparable to the Corsair revealed fundamental limitations in engineering capability, manufacturing capacity, and resource availability. Technical reports documented unsuccessful efforts to achieve bent wing configurations while acknowledging American technological leadership. German aviation development, increasingly focused on simplified designs, could not compete with American innovation and manufacturing excellence. The post-war influence of Corsair design principles included incorporation of bent wing concepts in advanced aircraft development programs worldwide. Engineering lessons learned from the revolutionary configuration influenced jet aircraft design, manufacturing techniques, and structural analysis methods. German post-war aviation development adopted American design principles, while acknowledging the technological leadership established through Corsair innovation. Training facilities developed for Corsair operations included specialized schools, technical training centers, and maintenance academies that created personnel capable of supporting sophisticated aircraft systems. These educational programs produced technicians, pilots, and support personnel with capabilities that German training systems could not match. American investment in human capital multiplied technological advantages through systematic personnel development. The combat effectiveness demonstrated by Corsair operations against both German and Japanese forces validated the aircraft's technological superiority across diverse operational environments. Kill ratios, mission success rates, and operational availability statistics documented performance advantages that enemy forces could not counter through tactical innovation or operational excellence. German aircraft, despite pilot skill and tactical expertise, could not achieve comparable combat effectiveness. Counterintelligence operations protecting Corsair technological advantages included systematic security measures that prevented enemy access to design details, manufacturing processes, and operational procedures. Comprehensive classification systems, personnel security programs, and facility protection ensured that revolutionary aircraft technology remained secure despite enemy espionage efforts. American security capabilities maintained technological advantages through systematic protection of industrial and operational secrets. The environmental adaptations required for Corsair operations in diverse theaters included modifications for tropical climates, high-altitude performance, and primitive base conditions. Engineering flexibility enabled rapid adaptation to operational requirements while maintaining the aircraft's revolutionary performance characteristics. German aircraft, designed for specific operational environments, could not achieve comparable adaptability to diverse combat conditions. Scientific research programs supporting Corsair development included aerodynamic studies, structural analysis, and performance optimization that continuously enhanced the aircraft's capabilities. University laboratories, government research facilities, and industrial development centers collaborated to maximize the potential of revolutionary aircraft design. German research capabilities, increasingly limited by resource constraints and facility destruction, could not maintain comparable scientific development programs. The manufacturing achievement of producing over 12,500 Corsairs demonstrated American industrial capabilities that established the foundation for post-war economic dominance. Each aircraft required sophisticated manufacturing processes, precision assembly techniques, and quality control systems that influenced industrial development worldwide. German manufacturing, simplified by wartime constraints, could not approach American technological sophistication or production efficiency. Medical services supporting Corsair pilots included aviation medicine specialists, high-G training programs, and specialized treatment facilities that address the physiological demands of high-performance flight. Flight surgeons understood the medical implications of the aggressive tactics that Corsair capabilities enabled while providing care that maximized pilot effectiveness. German aviation medicine, limited by traditional approaches and resource constraints, could not provide comparable medical support for high-performance aircraft operations. The technological revolution represented by the Corsair's bent-wing design established American aviation leadership that influenced military and civilian aircraft development for decades. Engineering principles, manufacturing techniques, and design philosophies developed for the revolutionary configuration became standard throughout the aviation industry. German aviation, forced to acknowledge American technological superiority, adopted American design principles in post-war development programs. The psychological impact of Corsair encounters on surviving German pilots extended beyond individual combat experiences to influence Luftwaffe morale and tactical doctrine. Recognition that American aircraft technology had achieved fundamental advantages that German engineering could not match undermined confidence in German aviation capabilities. Individual pilot reports of impossible American aircraft performance created widespread acknowledgement of technological inferiority that affected combat effectiveness throughout German aviation units.